Hello, this is the fourth and final lecture in the proof complexity talks for the Satisfiability Bootcamp. In this talk, we're going to discuss cutting planes and then the Clique coloring principle and Craig interpolation for obtaining lower bounds to cutting planes degree. We'll then cover Nullstellensatz and the polynomial calculus. These are polynomial-based proof systems. And finally, we'll cover automatizability as a separate topic mostly. Our treatment of these topics are pretty cursory. They give us the basic definitions, a few of the initial results, and just enough. Does not cover, however, the current state of the art in these areas, especially the cutting planes and Nullstellensatz and polynomial calculus portions. So let's start with cutting planes. Cutting planes is a propositional proof system based on reasoning with linear integer inequalities or integer programming. The classic work on this is done in the 60s and 70s. Clique Coloring and Turan proposed it as a propositional proof system in 1987. Variables are x1, x2, x3, etc. These are 0, 1 valued variables. We're interpreting 0 as false and 1 as true. Hence, they're essentially Boolean values, but interpreted as integers. Lines in a cutting planes proof are linear inequalities with integer coefficients, shown here as like a1 x1 plus a2 x2 plus ... a and xn greater than or equal to a0. And again, the ai's are all integers, but possibly negative integers. Clauses become inequalities. So if we're trying to refute a set of clauses, we transform them first to inequalities. So the clause x or y or z becomes x plus y plus z greater than or equal to 1. And these express the same condition given that we're interpreting 0 as false and 1 as true. Likewise, x or not y or z becomes x minus y plus z greater than or equal to 0. The idea here is we think of not y as being the same as 1 minus y. So we get x plus 1 minus y plus z greater than or equal to 1, which is the same as x minus y plus z greater than or equal to 0. Cutting planes, like resolution, is a refutation system. We start off with two types of initial axioms and then hypotheses. And the hypotheses are linear inequalities, and we're trying to refute that they all hold at once with integer solutions, especially 0, 1 valued solutions. So the logical axioms are xi greater than or equal to 0 and not xi greater than or equal to minus 1. And this reflects the fact that each xi has value either 0 or 1, so it's bounded between 0 and 1. Additional inferences are the addition rule and the division rule. The addition rule takes as hypotheses two linear inequalities and just directly sums them up together. So clearly the conclusion follows from the hypotheses. The division rule is as follows. We take an integer c greater than 0, and we assume that c is a divisor of a1 through an. So it's divisor of the coefficients on the left-hand side of the equation. And then from the sum of ai(xi) greater than or equal to a0, we can infer the sum of ai over c times xi greater than or equal to a0 over c, rounded up to the nearest integer. So on the left-hand side, the coefficients ai over c are integers because of the hypothesis that c is a divisor of ai. On the right-hand side, a0 over c may be fractional, but it gets rounded up to the nearest integer. And this is a valid inference because the coefficients are all integers. ai over c's are all integers. xi's are all integers, either 0 or 1. And so the left-hand side is an integer. And so if it's greater than or equal to a0 over c, it's also greater than or equal to a0 over c, rounded up to the nearest integer. And then we're trying to do a refutation. We're supposed to end up with a false linear inequality at the end, and the final line should be 0 greater than or equal to 1. And we can always get any inequality 0 greater than a positive number in this form by using the division rule. So as an example of how this works, suppose gamma contains the three clauses not x or not y, not x or not z, and also not y or not z. This expresses intuitively that no two of x, y, and z are true. And we'd like to re-express this using cutting planes in inferences. So first of all, these three clauses turn into inequalities. The first one's minus x minus y greater than or equal to minus 1. In other words, because 1 minus x plus 1 minus y is greater than or equal to 1, we get the first inequality. And similarly, the second one is minus x minus z greater than or equal to minus 1. And the third one is minus y minus z is greater than or equal to minus 1. If we add up using two instances of the addition rule of these things, we get minus 2 times x plus minus 2 times y plus minus 2 times z greater than or equal to minus 3. Now we can divide by 2, and we get minus x minus y minus z greater than or equal to minus 1. And this, of course, means intuitively the same thing as x plus y plus z less than or equal to 1. Now you can't write this latter inequality in a cutting planes proof. You have to use it in the form with the minus signs. But nonetheless, this is a more succinct way of expressing that no two of x, y, and z are true. And you'll notice we could not have derived this without using the division rule with its rounding properties. So a nice but simple theorem is that cutting planes has polynomial size refutations of the clauses expressing the negation of the pigeonhole principle. So let's just reformulate this as inequalities. The totality axiom says the summation over j of xij is greater than or equal to 1. Injectivity axiom says the summation over I of xij is less than or equal to 1. So you can derive these things similar to the argument on the previous slide. So now we get the summation over all variables xij is greater than or equal to n plus 1, and also the summation of all xij's is less than or equal to than n. What I mean by that is negating both sides of that. So the sum of the negative of the xij's is greater than or equal to minus n. And then we add those two things together to conclude that 0 is greater than or equal to 1. So that's a nice simple proof, and cutting planes is ideally suited to do it because it can just directly sum things up. Hence, as a corollary, resolution does not p-simulate cutting planes. And also, by the side comments earlier, constant depth Frege proof systems do not p-simulate cutting planes. Again, by the pigeonhole principle. On the other hand, we can go the other way to a certain extent. Cutting planes does p-simulate resolution, and the idea for the proof there is that a single resolution step can be easily simulated by using an addition rule and then a division by 2 rule. Actually, perhaps using several addition rules to round things up to 2, and then a division by 2 rule. And on the other hand, as shown by Gert, that cutting planes is p-simulated by Frege proof systems. And the idea for this theorem is that you can use this carry-save addition of the type we used earlier for summing vectors of integers for the pigeonhole principle proof to express with polynomial size propositional formulas in a Frege proof system the inequalities given by lines in a cutting planes refutation. And thus it becomes, once this is done, it's then fairly straightforward to simulate cutting planes by Frege proofs. On the other hand, for lower bound, Pudlock showed that for cutting planes, you do have exponential size proofs for the Clique coloring clauses. To talk about this, we first need to define the Clique coloring clauses. So the Clique coloring clauses are a set of an unsatisfiable set of clauses which are unsatisfiable by virtue of a graph on n vertices not being able to have both a clique of size m and a coloring of size m minus 1. So a clique of size m says there's m vertices which are all adjacent pairwise to each other, and a coloring of size m minus 1 says there's an assignment of m minus 1 distinct colors to all the vertices such that no two adjacent vertices get the same color. So you can't have both of these because there would be no way to color the vertices inside the clique of size m. So we're going to use variables p, q, and r attached with subscripts. The subscripts will be a, c, and I, and j, And A will range over M, the size of the clique. C will range over M minus 1, the number of colors. And I and J will range over vertices in the graph. So for each N, we get a distinct instance of the clique coloring clauses. So the meaning of the variables P, A, I is that vertex I is the 8th member of the clique. The variables Q, I, C are intended to say that vertex I has color C. The variables R, I, J is intended to say there's an edge joining the vertices I and J. And now we have clauses A expressing the existence of a clique and clauses B expressing the existence of a coloring. So the clauses A involve only the variables P and R. They don't need the coloring at all. The first types of clauses in them are the or over I of PAI. This is for A fixed, and this says that there's some I, such as I is the 8th vertex of the clique. And then the next clauses in APR are not PAI or PA prime or not PA prime I, which says that it's not the case that I is both the 8th member of the clique and the A primeth member of a clique. And the third types of clauses are not PAI or not PA prime J or RIJ. And this says that if I is the 8th member of the clique and J is the A primeth member of the clique, A is not equal to A prime, then there's an edge, that's RIJ, from vertex I to vertex J. So if these clauses are satisfied by some assignment, then we have a clique of size M. The clauses BQR express the coloring, and the first one is or over C of QIC, which for a fixed I, this says that vertex I is assigned some color C. And the next set of clauses are not QIC or not QIC prime, which says that each vertex is assigned at most one color. And the third clauses are not QIC or not QJC or not RIJ, which this says that if both vertices I and J are assigned color C, then there's no edge between I and J. So one thing to notice here is that the R variables appear only positive in the clauses APR, that is unnegated, and they occur only negatively, that is negated, in the clauses BQR. And that'll be important very shortly. So Krycek showed that any resolution refutation of the clique coloring tautology for m equal to the square root of n requires exponential size, in this case 2 to the omega n to the 3/4. And shortly after that, Pudlock showed that cutting planes likewise requires exponential size proofs, really refutations in both cases, for the clique coloring clauses. The two proofs have a similar strategy. They both use a Craig interpolation theorem, which I'll describe on the next slide what that means. And they use these known lower exponential lower bounds on the size of monotone circuits that distinguish graphs with large cliques and graphs with large colorings. For cutting planes, the second theorem, it was required to extend these bounds for Boolean circuits to real circuits, and I'll describe that in a little bit later. But first, let's talk about Craig interpolation. So Craig interpolation refers to a classic result, even in first-order logic, of defining interpolants. And this Craig interpolation now, in this setting, is the simplification of this down to propositional logic. So this work was done by the two papers already mentioned of Krycek and Pudlock, and earlier the first work along these lines was Bonet, Patazzi, Raz, and then Razbarov as well did a full version of it. So let's make the definition. We have two formulas, A involving variables P and R, and B involving variables Q and R. And we assume that the conjunction A and B is unsatisfiable. And we assume the only common variables in A and B are the indicated variables R. So a Craig interpolant for A and B, it's a predicate C of R, that is involving only the common variables R, such that for any setting to the variables R and P and Q, if C of R is false, then A of PR is false. In other words, for any setting the variables R, if C of R is false, then A of PR is unsatisfiable. And then conversely, for any setting the variables R, if C of R is true, then B of QR is unsatisfiable. And another way to say this is in terms of implication, which is how Craig initially stated in interpolation. We have, because A and B is unsatisfiable, that means that A implies not B. So these conditions on C means that A implies C, that's from not C implies A, and then C implies not B. So what we're getting here is if A implies B, we can interpolate or stick in the middle a C, and the C only depends on the common variables, the variables R, that occur both in A and B. And the theorem is that whenever A of PR and B of QR is unsatisfiable, there is a Craig interpolant C of R. And one easy way to take this is we can take C of R to be exists P A of PR, or for all Q not B of QR. And it's easy to check that that is a Boolean function that defines an interpolant. The problem here is we've got existential quantification, so we may not have a polynomial time interpolant, for instance, or some feasibly computable interpolant in the general case, and there's a lot of open questions here, of course. And but in some cases, we do manage to get polynomial time Craig interpolants. And this happens in particular when we have a resolution refutation of the set of clauses A of PR union B of QR. So the theorem is that we assume that the conjunction or the set of clauses A of PR, B of QR has a resolution refutation of size M. And then we further assume that all the variables R either appear only positively in the clauses of A of PR or only negatively in the clauses B of QR. If all these conditions hold, then there's a Craig interpolant, which is computed by a monotone Boolean circuit of size order M. So monotone Boolean circuit means the following. The inputs of the variables R, and they're not negated because it's monotone, and the gates in the circuit are just ands and ors. And the total number of gates is order M, and M is the number of steps in the resolution refutation. So as an application, the Clique coloring principles require exponential size resolution refutations, as we'll discuss on the next couple slides. So here's a sketch of the proof of the Craig interpolation theorem. Basically, the resolution refutation R transforms directly into the desired monotone circuit. We take each clause in the refutation. So we view the refutation as a DAG, and we're going to take that DAG structure and faithfully transform it into a monotone circuit. So what we're going to do is define, for each clause C appearing in the proof, we're going to have a gate G of C. And G of C is going to have the property that for any assignment of variables, look at the bottom of the screen here, for any assignment of the variables to, and any partial assignment that falsifies all the literals in clause C, if G sub C is false, then there's some clause of A that is false. And if G sub C is true, then there's some clause in B that's false. So G sub C is like a pointer that says, assuming C is false, then G of C will either say something in A is false, or will say something in B is false. And we now just go inductively through the resolution refutation and construct a circuit. So we start off with initial clauses from A of PR. We can just take G of C equal to false, because here it's trivially an interpolant because G of C is false, and we're saying that we're assuming that any partial assignment that falsifies A, that an A clause must falsify some A clause. And similarly for a B clause as initial clause, G of C is true, because if that clause is falsified, then there's some B clause that's falsified. And then without going into too many details, if we resolve on a variable P, that's one of the variables that occurs in A but not in B, we replace that resolution inference by an OR gate. So the G sub CD, the conclusion of the resolution inference, is just the OR of the G sub PIs and the G sub D PI bars, which are the values for the hypotheses of the resolution inference. Something dual works for resolving on the variables Q that appear in B but not A. We just replace that inference by an AND gate. And then if we resolve on a variable R, it's a little more complex. Here we either use G sub CD, the G for the conclusion of the resolution inference. It's either R or G sub CRI and G sub DRI, or it's something dual, G sub CRI or RI and G sub DRI. And the point is that if R is monotone in A, appears only positively in A, or monotone in B by appearing only negatively in B, we can choose one of these or the others and still maintain the interpolation property. So I'll let you work that out on your own. I'm not going to try to go through all the details here, but the important point here is that the monotone circuit defining a Craig interpolant is just read directly off of the resolution refutation. And now we get the theorem that I already mentioned for resolution, so that any resolution refutation of the Clique coloring tautology for m equals n1/2 requires size 2 to the omega n to the 3/4. So we just apply the Craig interpolation theorem to the Clique coloring tautology, assuming that there's a short resolution refutation for the Clique coloring tautology. So the variables R encode the edges of a graph. If the Craig interpolation property tells us that if there's a short resolution refutation of size S, we get an interpolant, and if the interpolant's false, it means that A of PR is unsatisfiable. In other words, that G does not have a clique of size M. If C of R is true, then B of QR is unsatisfiable. In other words, G does not have a coloring of size M-1. But on the other hand, we know from results of Razborov and strengthened by Alon-Bapana that any monotone Boolean circuit that distinguishes between graphs with large cliques and graphs with large colorings must have exponential size. So it follows immediately then that the resolution refutation must have exponential size. And that's the sketch of that proof. And the general framework of the proof for cutting planes is similar. So Pudlock extended the Craig interpolation theorem to cutting planes. Here again, we assume that a set of clauses APR and BQR have a cutting planes refutation of M steps, and that the variables R appear only positively in the clauses APR or only negatively in the clauses BQR. The conclusion is there's a Craig interpolant, which is computed by a monotone real circuit, not a Boolean circuit anymore, a real circuit of size M to the order 1. And a real circuit means a circuit where the values are on the wires in the circuit are real numbers. The circuit has arbitrary unary and binary gates that take as inputs real numbers and output a real number, but must compute monotone real functions. So monotone real function means that if you increase the value of one of the inputs, you cannot decrease the value of the output. And then the Razborov-Alon-Bapana lower bounds, the proof can be reworked to show the same type of lower bounds for real monotone circuits. And then as a corollary to the interpolation for Clique coloring, as a corollary to the interpolation for cutting planes, and the lower bounds on real monotone circuits for separating graphs with large cliques from cliques of size M from graphs with colorings of size M-1, we get that cutting planes does not have polynomial size refutations. In fact, it needs exponential size refutations for the clique coloring clauses. expressing that a graph is both k-colorable and has a k+1 clique for appropriate values of k. So now we're going to shift gears a little bit and talk about two algebraic proof systems. First one is the Nullstellensatz proof system. This was introduced by Beam and Pagliazzo, Krycek, Potassi, and Pudlock. We work generally over a finite field, characteristic P. Variables x1, x2 are 0, 1 valued. And now the lines in the proof are polynomials. So a polynomial f is identified with the assertion that f equals 0. And we refute a set of initial polynomials, fj, by giving polynomials gj and h, such that the following equality is a valid polynomial equality. So we have that the initial polynomials fi times g, the sum over j of fj times gj, plus the sum over xi squared minus xi times hi is equal to 1. And this equality, so the values xi take on values 0, 1. So for xi equal to 0, 1, we certainly have xi squared minus xi equals 0. And if this equality holds, there's no way to set the values of x1, x2, x3, etc., so that the fj's are all simultaneously equal to 0. Because if there were such a way, then the left-hand side would just be would be equal to 0 for those settings to the variables xi, and the right-hand side, of course, would be 1. So what we're getting here is a Nullstellensatz refutation as a kind of static proof. You write out just a single equality, and if this equality holds, there's no way to simultaneously set all the input polynomials, the fj's, to 0. So it serves as a refutation to the assertion that the fj's are all equal to 0 at once. So we can translate clauses into polynomials, and then Nullstellensatz is known not to simulate resolution. It becomes a proof system, but the converse is true as well. Resolution or even constant Frege systems do not simulate Nullstellensatz. So for this, it's traditional to work with the degree of Nullstellensatz proofs rather than their size. It's just easier and more natural in many ways to work with the degree. And in general, we're going to work over a field of finite characteristic P. And a couple sample classic lower bounds here on degree is that there's these counting mod Q principles where Q is not a power of P, and there are not constant degree Nullstellensatz refutations of the counting mod Q principles in this case. And this is due to Beam and Pagliazzo, Krycek, Potassi, and Pudlock. And stronger result then is linear lower bounds on the degree for the pigeonhole principles. And this is due, the first lower bounds, such lower bounds given by Beam, Cook, Edmonds, and Pagliazzo, Potassi, and the strong linear lower bounds given by Razborov. So we have very nice degree lower bounds on Nullstellensatz, as well as we can get size lower bounds. I don't want to say too much more about this except to say that there's lots of applications to Nullstellensatz lower bounds. This includes separation results for constant depth Frege proofs. This was the initial reason for developing Nullstellensatz, actually, especially, and also separations for subclasses of TFNP, the total NP functions. More recently, they've been used Nullstellensatz lower bounds have been used to get lower bounds for monotone span programs, and also to get lower bounds for cutting planes refutations via lifting theorems. Another related proof system is the polynomial calculus. The polynomial calculus has the same type of syntax as the Nullstellensatz system, but it's a so-called dynamic system rather than a static proof system. It starts with hypotheses, and then it combines them with addition and multiplication. So think of the hypothesis F in this inference on the right, meaning F equals 0, and the conclusion F times G, meaning F times G equals 0. And the hypotheses f and g on the left-hand side are f equals 0 and g equals 0, and the inclusion is f plus g equals 0. And a polynomial calculus refutation of a set of polynomials, it's a derivation of the polynomial 1 starting with the fj's and the polynomials xi squared minus xi. And so the polynomial calculus, the Nullstellensatz systems can refute, of course, exactly the same sets of polynomials, but a polynomial calculus refutation can be substantially shorter and have substantially smaller degree due to the cancellation of monomials in intermediate steps. So one sample result here, and a rather strong result for the polynomial calculus, any polynomial calculus refutation of the polynomials expressing the negation of the pigeonhole principle must have degree linear omega of n in n. So I want to conclude this talk with a different subject of automatizability. So automatizability relates to the hardness of proof search, which of course is a crucial issue for satisfiability algorithms. We say that a proof system is automatizable, and we mean typically in polynomial time, if there's a procedure which, given a formula phi as input, produces a t-proof, a proof in that proof system, of phi within time, the runtime to produce this t-proof, is bounded by a polynomial of the size of the shortest t-proof of phi, if there is one. So it doesn't have to be polynomial runtime in the size of phi itself. It just has to be runtime in the size of the shortest t-proof of phi. Surprisingly, a related concept is the notion of feasible in interpolation, which says that you can get feasibly Craig interpolants. So if a proof system T has feasible interpolation, if there's a polynomial time procedure C, such that if P is a T-proof of not APR and BQR, then CPR, this is the results of the polynomial time computation, is a Craig interpolant for A of PR and B of QR. So rather nice result. Bonnet and Passy-Raz noted that if T is automatizable, then T has feasible interpolation. Another nice result is due to Kryacek and Pudlock. The extended Frege proof system does not have feasible interpolation and thus is not automatizable unless the RSA encryption function and the discrete logarithm encryption function can be inverted in polynomial time. So one doesn't expect those can be inverted in polynomial time. We suspect they're secure. And so based on those conjectures, one would conclude that it's expected that the extended Frege system is not automatizable. A similar result obtained by Bonnet-Passy-Raz shows that Frege systems do not have feasible interpolation and thus are not automatizable unless Blum integers can be factored in polynomial time. Blum integers are products of two primes, each congruent to 3 mod 4. And again, this is thought to be a hard problem to invert or to factor such integers. And then finally, there's been some very striking recent results just in the past couple years under the assumption that P is not equal to NP. First of all, Atsarius and Miller showed that if you assume P not equal to NP, it follows that resolution is not automatizable. So there's no way to search for polynomially length optimal resolution refutations unless P equals NP. Subsequent to that, it was shown that cutting planes is not automatizable, and also that the Nullstellensatz proof system and the polynomial calculus proof systems are not automatizable. Again, in both cases, under the assumption that P is not equal to NP. Of course, if P equals NP, then every system is automatizable. You can essentially ask bit by bit, does that for a shortest possible proof. So these are somewhat negative results, although not so bad, because it's just saying although resolution or cutting planes and Nullstellensatz and polynomial calculus in some cases are strong systems, it may still be hard to find these proofs. A positive result, though, is due to Beam and Potassi, that says that tree-like resolution is automatizable in quasi-polynomial time. So in other words, we let S be the size of the shortest tree-like resolution refutation, and n is the number of variables. Then in time approximately n to the log s, it's possible to find some tree-like resolution refutation. For resolution, these methods give a much worse time bound of n to the square root of n log s. But these represent more or less the state of the art for automatizability. That's the end of this talk. Thank you very much.